Welcome back to the Deep Dive. When we think about preparing humans for spaceflight, we often picture astronauts in peak physical condition. But what does it really take?
Yeah, that physical part. It's important, sure, but it's really just the tip of a massive iceberg.
Right.
Absolutely. We've pulled together a stack of sources that reveal astronaut training as this incredibly intricate, multifaceted process happening all around the globe. It's a real deep dive into human readiness for, well, the ultimate extreme environment.
Okay, let's unpack this then. Our mission today is to, cut through the complexity and give you a clearer picture. We'll explore the different stages of training, the intense physical and psychological challenges astronauts face, how that training directly addresses those hurdles, and the surprising growing role of cutting-edge tech like virtual reality.
Yeah, that VR part is fascinating.
So by the end of this, you should have a solid handle on what it means to truly prepare a human for space.
Exactly. And, at its core, astronaut selection isn't really separate from training. They're integrated. The whole process is designed to qualify candidates and build their capabilities, both for the general environment of space and for the highly specific tasks of their assigned mission.
So how does this journey typically unfold once someone actually gets selected? Is there a standard path they follow?
There is, generally speaking. It's broken down into 5 key objectives or phases, you could say. It starts with basic training, which is foundational,
Okay.
moves into advanced training, then becomes highly specific with mission-specific training. Once they're assigned to a flight and, about to head up, there's onboard training for systems they'll use right there in space. And finally, proficiency maintenance. That's throughout their career, just keeping critical skills sharp.
Basic training, I imagine that's covering a ton of ground just to get them up to speed on the fundamentals.
Oh, absolutely. It's surprisingly broad and deep. Candidates dive into medicine, languages, particularly Russian, which is crucial for ISS operations.
Yeah, right, the international aspect.
Exactly. Robotics, even some piloting basics for certain roles. They learn space system engineering, the fundamental organization of space systems. And yes, they have to master a significant amount of aerospace acronyms just to communicate effectively.
Wow. That list alone sounds pretty daunting. And I was really struck by something I saw in the sources. Despite all this rigorous selection and training, a huge percentage of astronauts still get space sick.
It's a fascinating vulnerability, isn't it? Despite all the screening and conditioning, somewhere between 60 and 80% of astronauts encounter space motion sickness.
60 to 80, that's high.
It is. Symptoms can range, from just feeling pale and sweaty to actual vomiting and loss of appetite. It usually hits within minutes of reaching orbit because of that abrupt shift in gravity perception.
Right.
But what's critical here is that while it's common, it rarely lasts more than a couple of days on orbit, and the training includes being expected to overcome it, to push through and continue working.
Wow. So after mastering those basics and pushing through initial physical stuff like motion sickness, you mentioned advanced and mission-specific training. How do those phases build on that foundation?
Well, advanced training drills deeper into specific spacecraft systems, enhances skills relevant to positions they might be assigned to, like, say, particular engineering roles or specific science duties.
Right.
Then mission-specific training is the longest phase, typically around 18 months for crews heading to the ISS. This is where everything becomes really tailored. They learn the exact procedures for their specific experiments, the equipment they'll use, the operational tasks planned for their specific time and space.
And throughout all these demanding phases,
Yeah.
Keeping the astronauts healthy, physically and mentally, that has to be a constant focus, right?
Absolutely paramount. Training isn't just about technical skills, it's deeply invested in physical and mental well-being. This focus is there right from the initial selection, continues through all the training phases during the mission itself, and it's critical during the post-flight recovery period, too.
Makes sense. And that final phase you mentioned, proficiency maintenance. Is that like ongoing refreshers, keeping those skills sharp?
Precisely. It's about ensuring they consistently maintain minimum performance levels in key areas, even if they're not actively assigned to a mission at that moment. This includes critical skills like EVA, extravehicular activity, spacewalks,
Right.
robotics, maintaining language fluency, keeping up their diving skills, which is used a lot in spacewalk training simulations and flight training.
Okay, so we've got the training process mapped out. But what are the biggest physical and environmental hurdles astronauts actually face out there? And how does all this preparation really equip them for that?
Well, the challenges start the moment they strap in, really. Launch and landing expose them to significant G-forces. Then suddenly they're in microgravity. As we discussed, space motion sickness is common, quick onset. There's also the risk of orthostatic intolerance, basically, difficulty standing upright when they get back due to blood pooling, and potential cardiovascular events. Now, astronauts are highly screened to remove pre-existing conditions, but spaceflight itself impacts the cardiovascular system because of those fluid shifts. This can make simple things like just getting out of the spacecraft unassisted upon return difficult after a long mission.
So training addresses not just getting to space, but handling the environment once they are there and even coming back safely.
Exactly. On-orbit operations training prepares them for everything. We can kind of think of this in two buckets, internal and external events.
Okay.
Internal is mastering the spacecraft itself, knowing all the engineering systems like propulsion, thermal control, life support inside and out.
Yeah.
It's also deeply understanding orbital mechanics, how to conduct scientific experiments, Earth observation, astronomy, all crucial, especially in a place like the ISS.
Right.
And they train rigorously for hazardous scenarios. What do you do if life support fails? Or there's a depressurization? Or a fire? Plus, training for mission success tasks like actually performing EVAs, running complex experiments, or even manual piloting if needed.
And external events.
Yeah.
That sounds like literally living and working outside the spacecraft.
Yeah, that's dealing directly with the space environment and its effects on the human body. Adapting to microgravity isn't just about floating. It causes spatial disorientation, motion sickness, vertigo, especially initially. Then there's isolation and confinement. Being in a small space for months is a significant psychological stressor, known to potentially limit performance. So training includes specific preparation for that psychological challenge.
That must be huge.
It is. And then there's radiation, a silent but serious threat. While the long-term effects are still being studied, a trip to Mars could expose astronauts to a dose maybe 1,000 times higher than on Earth in a year. Future training has to include advanced methods for radiation protection and mitigation.
You mentioned science earlier. Missions like the ISS are basically orbiting labs. How does training make sure astronauts can actually do complex science effectively with, limited real-time communication back to Earth?
Training for science experiments is absolutely vital. You want to maximize the scientific return on investment, right?
Of course.
Time and communication bandwidth on orbit are limited resources, so astronauts need to be incredibly familiar with the protocols, the equipment. It's a collaborative process, really. It starts with the scientists on the ground who brief the trainers.
Okay.
And those trainers then prepare the astronauts, often at facilities like the European Astronaut Center or EAC. For human experiments, where the astronauts themselves are the subjects, they have to actively choose to participate. And they undergo testing before, during, and after the mission to get baseline data and track changes.
This whole thing is so international, especially with the ISS. How do the different global space agencies approach this complex training? Is it all standardized now, or do they have their own unique ways?
Well, while the ISS partners definitely share common goals and often train each other on their specific modules or systems, each major space agency absolutely has its own established approach. They have their own history, their own facilities.
Okay, so let's break that down. How does the U.S., NASA, handle it?
Right. So in the U.S., NASA's candidates, or ASCANs as they're sometimes called.
ASCANs.
Yeah, astronaut candidates. They undergo up to 2 years of initial training. Basic training alone covers something like 16 technical areas, everything from life support systems to space physiology and medicine. It includes mastering Soyuz and ISS systems, rigorous flight safety, survival training, land and water scenarios.
Wow.
Pilots also train on T-38 jets. On top of the technical stuff, there's extensive professional development, cultural sensitivity training, and of course, Russian language training for ISS ops.
That's packed.
Then advanced training involves working with life-size models, simulation mock-ups, and then there's the really intense 3 months just before launch called intensive training. That's heavy on flight-specific simulations, joint training with flight controllers, detailed mission planning, final experiment prep.
And NASA has some really iconic training sites, don't they? I think people have seen pictures of some of them.
Oh, absolutely. The Space Vehicle Mock-Up Facility, the SVMF, it's basically a giant warehouse crammed with full-scale models of the ISS, Orion, other vehicles. They use it for practicing maintenance, emergency procedures, comms.
Okay.
For microgravity simulation, there's the famous KC-135, the Weightless Wonder, or less flatteringly, the Vomit Comet.
Right, the plane that does the dives.
Exactly. Flies those parabolic arcs to give about 20-25 seconds of weightlessness at a time. Then there's the PABF, the Precision Air Bearing Floor. Think of a giant air hockey table. It simulates a low-friction environment for practicing moving really large objects in space. But probably the most famous for spacewalks is the Neutral Buoyancy Lab, the NBL. It's this massive swimming pool, just enormous, containing full-size mock-ups of the ISS and other spacecraft. Astronauts spend countless hours underwater there, simulating the weightlessness and procedures of EVAs.
That pool sounds incredible. So what about Europe? How does ESA approach it?
Over in Europe, the main hub is the European Astronaut Center, EAC, in Cologne, Germany. Their basic training takes about 16 months. It covers orientation to all the partner nations and agencies, space laws, policies, the tech and science basics, ISS operations, learning about servicing spacecraft like Soyuz, ATV, HTV.
So similar basics, but with a European focus.
Right. Plus robotics, rendezvous procedures, Russian language, and essential human behavior studies for confined environments. They also do a scuba course as sort of basic prep for EVAs before they head over to NASA's NDL for the full-on spacewalk training.
Ah, okay, so they use the NBL too.
Yes, for the high-fidelity stuff. Then ESA's advanced training is another year, focusing on in-depth ISS systems and more advanced science, and that happens across various partner sites. The actual flight assignment usually comes after that phase. Increment-specific training, similar to NASA's, is about 18 months pre-flight, highly tailored, covers their exact tasks, equipment, lots of off-nominal situation training, and mission experiments.
Got it. And Russia, they have a long history here.
They do. They train at the historic Yuri Gagarin Cosmonaut Training Center, Star City, just outside Moscow. Their path involves about 2 years of general space training classes, survival training, final exam. Then comes a year of group training where cosmonauts specialize in either Soyuz or ISS systems and work on professional skills.
Okay.
After that, about 1.5 years of crew training, focusing on detailed procedures, specific ISS training, and English language proficiency is key now. And given the collaboration on ISS, Russian cosmonauts also spend significant time training in other partner countries, too.
Makes sense. How about Japan?
Oh.
JAXA.
Japan, JAXA, historically relied quite heavily on NASA for training. But now, the Tsukuba Space Center is really their central hub. Their structure is pretty similar to the other ISS partners now. About 1.5 years of basic, then 1.5 to 2 years of advanced training, done both at Tsukuba and partner sites. Then increment-specific training back at Tsukuba.
Do they have their own NBL equivalent?
They do. They have the Weightless Environment Test System, or WETS. It's their own neutral buoyancy facility, specifically designed for training on their Kibo ISS module mock-up. Tsukuba also has medical facilities, an isolation chamber for psychological training, and a hypobaric chamber for pressure scenarios.
Okay, interesting. And China, they have their own independent program, right?
Yes. China, with its Shenzhou program, has a distinct approach. They select candidates primarily from the Air Force based on quite specific criteria: age, flight hours, education, height, weight. Their training has several stages. Stage 1 is about a year. Basics, physical conditioning, psychological prep. Stage 2 takes nearly 3 years, focusing on Shenzhou piloting and systems, both nominal and emergency procedures. Stage 3 is about 10 months of mission-specific training using high-fidelity trainers and their own neutral buoyancy facility at the Astronaut Center of China, ACC, in Beijing.
They have an NBF, too.
Yep. They also use vacuum and low-temperature chambers for EVA simulation and employ physical conditioning like centrifuge training and microgravity flights. Historically, they even use facilities in Russia for some of that parabolic flight training.
And finally, India. ISRO is developing its own human spaceflight program.
That's right. India is preparing its GandM program. While it's still pending its first crewed flight, their training plans draw lessons from past cooperation, like Rakesh Sharma's joint mission with the Soviets back in the 80s. They're looking to collaborate with NASA and Roscosmos. They plan to establish a domestic training facility near Kempegowda International Airport in Bengaluru, including chambers for simulating radiation, thermal cycling, acceleration. But it's expected their first crewed mission training will likely involve significant time at facilities in the U.S. or Russia, leveraging that existing expertise.
That's a truly global picture of how things stand now.
Yeah.
So let's look ahead. The future involves things like suborbital tourism, which is different, but also, critically, those long journeys back to the moon, eventually to Mars. How does training need to change for those vastly different kinds of missions?
Yeah, good question. For suborbital tourism, much shorter flights, not reaching orbit, private companies like Virgin Galactic, Blue Origin, Xcore Aerospace, they're developing their own, often proprietary training programs. These are tailored to their specific vehicles and, frankly, the customer experience, much less intense than orbital training.
Right, different goals entirely.
Exactly. But for long-duration missions, like staying on the moon for extended periods or the multi-year journey to Mars, the training demands just explode. Astronauts won't have large ground support teams available in real time due to communication delays.
The light speed delay, yeah.
Precisely, which means they need immense versatility. They'll have to be a doctor, a scientist, an engineer, a technician, a pilot, maybe even a geologist, all rolled into one small crew. And there will be a massive, massive focus on psychological readiness.
How so?
Training for deep autonomy, the intense isolation, the confinement, the potential monotony of being millions of miles from Earth for years. You can draw parallels, and researchers do, between the psychological challenges of a Mars mission and what crews experience on long submarine deployments or in those remote Antarctic research bases.
That makes complete sense. It's not just about fixing a system or doing an experiment anymore, but about keeping the crew functioning together, mentally healthy, in extreme long-term isolation.
Exactly. And research is actively exploring mental health support tools for these scenarios. The sources mention systems like Ansible. It uses virtual reality to provide, like, calming natural scenery or facilitate socialization with Earth or other crew members virtually.
Oh, interesting.
There's also the Virtual Space Station program developing modules for conflict management training, even virtual therapy sessions. Think about this. A typical 6-month ISS mission requires maybe up to 5 years of training beforehand.
5 years for 6 months. Wow.
Yeah. That duration is likely to expand significantly for missions lasting 1, 2, 3 years like Mars. The ISS itself could potentially serve as a long-duration training facility in the future, let crews experience prolonged isolation and self-sufficiency closer to home before they make the big trip.
And those analog environments you mentioned, places on Earth that simulate off-world conditions, they'll still be vital, right?
Right, definitely. Places like NASA's Nemo undersea habitat, the Desert Arat sealed tests, the Hot and Mars project up on Devon Island in the Arctic, they remain crucial. They provide realistic, challenging environments for practicing complex tasks like geology surveys, operating rovers or equipment, even simulating asteroid mission procedures underwater where neutral buoyancy mimics some aspects of microgravity or reduced gravity EVAs.
Okay.
And another key area for future training, especially on these long missions, is human-robot interaction. Robots are going to play a much bigger role as assistants, explorers in hazardous areas. We already have Robonaut 2 on the ISS as an early example.
Right.
Future crews will need specific training, not just in interacting effectively across cultures within the human crew, but also in seamless collaboration with their robotic partners.
So future astronauts need to be incredibly flexible, adaptable, able to integrate completely new kinds of team members, even non-human ones.
They absolutely will. The training for these longer, more autonomous missions needs to be inherently versatile. It needs to be easy for crews to learn new things on the fly, adapt procedures as situations change, and improvise solutions when they're millions of miles from immediate help. Considering crew dynamics, crew size, the kinds of activities over a multi-year span, these are all crucial parts of that preparation.
Okay, let's zoom in on a technology that seems increasingly vital across all these areas you've mentioned. Virtual reality. How has VR actually been used in astronaut training, and what are its real advantages and maybe disadvantages?
Right, VR. It started gaining commercial traction back in the 1990s, and its potential for astronaut training was recognized pretty early on. Initially, it was used for things like enhancing communication between someone operating a robot arm and an astronaut doing an EVA,
Okay.
and also to replace some of those huge, cumbersome physical mock-ups of spacecraft systems. NASA's Raven system in the 90s, for example, used VR for Hubble Space Telescope servicing training and helped evaluate how effective VR could be compared to other methods.
And the tech has come a long way since the 90s.
Oh, massively. The hardware has improved dramatically, higher resolution displays, better tracking, lighter headsets. This has led to much wider applications. It's now used not just for procedural training, but also for mission planning, collaborative design work, problem solving, visualizing complex data. We even saw that specific example in the sources of astronauts Marshburn and Wolf using VR right before a spacewalk, just for a final mental run-through.
So how is VR actually integrated into the current training flow day to day?
It primarily supplements the physical training and the big mock-ups. You'll find it used in various facilities in the SVMF mock-up facility we talked about, in dedicated virtual reality labs or VRLs, and even integrated into the underwater NBL training.
Underwater VR, how does that work?
Yeah, they can wear waterproofed headsets down there to overlay graphics or instructions onto the real physical mock-up, adding visual cues to the physical simulation. In the VRL on dry land, they use programs like DO, that stands for Dynamic Onboard Ubiquitous Graphics. It's this highly detailed 3D model of the ISS exterior. Astronauts put on a headset, haptic gloves maybe, use motion tracking, and they can virtually float around the station, practice routes, grab virtual handrails, manipulate virtual objects.
That sounds cool.
There's also fascinating tech like the Charlotte robot. It uses a system of cables and complex physics calculations running in the background to simulate the inertia and forces you'd experience trying to move or interact with equipment in microgravity. It lets you practice manipulating objects without them just floating away, but also without the drag of water, like in the NBL.
So you get a feel for the physics.
Exactly. They can train complex tasks individually or with a partner in these VR setups. And even commercial companies like Boeing use VR extensively for training pilots and crews on their Starliner vehicle, things like docking procedures or emergency egress simulations.
That sounds incredibly sophisticated. What are the big advantages that VR brings to the table compared to purely physical methods then?
Well, one major advantage is helping astronauts overcome visual reorientation and spatial disorientation. You know, those confusing feelings when you lose your sense of up or down in microgravity. VR training for this is less gear intensive and, frankly, more economical than spinning someone in a centrifuge repeatedly.
Right.
Mixed reality setups, which blend virtual elements with the real world, can actually reduce the simulation sickness sometimes associated with pure VR and allow for more natural movement. And studies have shown really positive results. Astronauts performing tasks faster, reporting significantly less nausea after VR training specifically geared towards these orientation challenges.
That's a tangible benefit.
It is. And what's really fascinating is that VR's utility isn't limited to ground training. It can potentially be used on orbit for proficiency maintenance. Let astronauts quickly refresh procedures for a task they haven't done in a while, or practice for an upcoming EVA.
Ah, okay, training in space itself.
Exactly. And crucially, it's showing real promise for mental health support during long isolation. Virtual simulations of, say, walking in a forest or social scenarios could help mitigate stress and maintain psychological well-being in that confined spacecraft environment. Plus, it's excellent for building a truly intuitive spatial understanding of complex layouts like the ISS. It goes beyond just studying diagrams or walking through the physical mock-ups. That DOUH program, for instance, even it simulates visual phenomena like the blooming effect, where bright stars seem to enlarge as your eyes adapt to darkness, adding another layer of realism that really aids spatial awareness before you even get there.
Those psychological and spatial benefits sound huge. But given the complexity you describe with things like the Charlotte robot, there must be some significant disadvantages or limitations too.
Oh, there definitely are limitations, especially with current tech. VR, as it stands, cannot fully replicate the deep psychological and emotional stress of actually being in space. There are no real life or death consequences for errors in a simulation, right? And it doesn't induce those visceral feelings like claustrophobia you might experience in a truly confined spacecraft over months.
Yeah, the stakes aren't real.
Exactly. Cost is also still a factor, especially for these high-fidelity systems used in astronaut training. They require expensive supplemental equipment, specialized trackers, haptic interfaces that aren't mass-produced like commercial VR gear. The necessary facilities and specialized gear add to the drawbacks, too. Systems like Charlotte or the high-end VRLs require dedicated, costly facilities, and there might be inherent limitations. Charlotte is tethered by cables, for example, and a VRL might only have a few training stations available. Specialized gear like haptic gloves, things like the GVX gloves mentioned, while improving, can still be uncomfortable, limit natural hand movement, and they're often still under development, kind of clunky. And achieving really realistic tactile feedback across the whole body requires expensive full-body sensor systems. Without them, your ability to truly feel and interact intuitively with the virtual environment is significantly reduced.
So lots of potential, but still some hurdles to overcome. As the technology keeps advancing, Where do you see VR heading in the future of astronaut training?
Well, the primary focus for future development seems to be really improving the simulation of microgravity itself. Current methods, even sophisticated ones like the Charlotte robot or the NBL, have limitations, or they can be uncomfortable, or don't quite capture the feeling. Think about bungee cords used in some partial gravity simulations they pull. They don't let you float freely.
Yeah, not the same.
Not the same at all. The big goal is increasing immersion and fidelity to the point where the lines between the real and virtual truly blur, allowing for much more realistic and effective training for maneuvering, tool handling, and just generally interacting in zero or reduced gravity environments without necessarily needing the giant pool or complex robotics for every single task.
Well, we've truly taken a deep dive today into this incredible, demanding world of astronaut training. From the intense physical and psychological conditioning to mastering incredibly complex systems and leveraging cutting-edge technology like VR, it's just clear that getting a human ready for space is a profoundly detailed and continuous process.
It really is. It's a process built on, centuries of human exploration and engineering, constantly adapting to the known challenges of space while trying, always trying, to prepare for the many unknowns. And it's all aimed at ensuring the well-being of the crew and the ultimate success of humanity's ventures beyond Earth.
Hopefully, this deep dive has given you a much clearer picture of what it truly takes to earn those astronaut wings and the astonishing level of preparation involved in every single mission.
And, as we set our sights on increasingly ambitious goals, like establishing a sustainable presence on the moon or embarking on that long, long journey to Mars, it really raises a fundamental question, doesn't it? How much of this intense, hands-on, sometimes uncomfortable analog training can truly be replicated or maybe even eventually replaced by increasingly sophisticated virtual and simulated environments? And beyond that, what entirely new forms of preparation will be demanded from future space explorers who will be working not just with their human crewmates, but in close daily collaboration with advanced robots and potential even sophisticated AI systems? What does that training look like?
A lot to think about there. Thank you for joining us for this deep dive.